So the next topic that we're going to consider is high-resolution mass spectrometry and how this type of instrumentation can help determine between different molecular formulas that may have the same molecular weight. So high-resolution mass spec allows mass spec to be measured with up to 4 decimal places. So the masses of like a proton and a neutron are generally not whole number integers. So a proton weighs 1.0073 AMUs and a neutron is 1.0086. So we can see that a carbon-12 atom weighs exactly 12 AMUs because that's by definition. But all the other atoms have slightly different molecular or atomic weights. So if we had a molecular formula that had the molecular weight where a low-res instrument would tell us the molecular weight was 60, we can have all these potential different molecular formulas. 60 AMUs can represent CH2NO2, which weighs 60.0085, or CH4N2O, which weighs 60.0324, or CH6N3, which weighs 60.0563, and so on. So you can see how these different molecular formulas can all be represented by 60 AMUs. And if we had a low-res instrument, we wouldn't be able to tell the difference between them. But with a high-res instrument, we can get 4 decimal places that can tell us the difference between these different molecular formulas, because we would know our atomic mass to 4 decimal places, and so we could just look this number up on a chart and we could reference that back to the correct molecular formula. So, for example, this instrument can help us determine the difference between these two, C5H8O and C6H12, which both have 84 AMUs. And in fact, the information is not in the book. I'm going to look it up real quick in my little table. 84 AMUs. Okay, so C5H8O weighs 84.0575 AMUs. 84.0575, and C6H12 is 84.0939. So you can get charts that let you cross-reference these different molecular formulas. So if you knew that your mass was 84.0939, then you could go back and look that up in a chart under 84, so it's going to be listed under 84, and it would tell you that you have C6H12 as your molecular formula. So you wouldn't, if you had this high-res instrument, you don't even have to calculate the molecular formula. And you can see here that how the different isotopes contribute to the molecular weight. So if you wanted to calculate your AMUs to the exact molecular formula, you could do that as well, you know, knowing how much, say, hydrogen atom weighs, oxygen weighs, and carbon weighs. So you could calculate your molecular formula. So you could calculate the difference between C5H8O and C6H12. But generally, if you have one of these instruments, you're going to have a table where you can actually look this information up. Okay, so the other application for mass spectrometry, as I mentioned earlier, is as a detective for gas chromatography, as a detector for gas chromatography. So gas chromatography is a powerful technique that is used in chemistry labs for separating samples. So if you had, say, a sample of blood or urine, you could extract the organic components with an organic solvent and then inject that into your gas chromatography instrument, and so it's going to go into a capillary column that will separate your sample into its different individual components. Okay, after it will leave then the GC and head into the MS part, the mass spectrometer part, going through the electron beam and the ion sorting region and hitting the detector. So this detector, this whole thing here is in fact our MS. So that's where the term GCMS come from. So we separate the sample into its individual components, and each of those components gives us a different mass spectrum. Each of those components would have its own mass spectrum. So you could click on each of those components in your gas chromatograph, and that would bring up in the computer its respective mass spectrum. So let's see what that looks like. This is what a gas chromatogram looks like. So you can use a GC on its own. You can put in some standards and you can measure the retention time. So the retention time, as we did TLC in the lab, is going to be relative to the affinity for the column for each one of those molecules. So the molecules are going to have an affinity for that column, and their relative affinity is going to affect the amount of time then that they spend on the column. So the affinity for the column is what gives us this separation. So we get our sample. In this case, our sample had 5 components, and so those 5 components are going to be separated into their individual peaks, and they're going to each have their own retention time. And so we could use standards to determine what our components were by comparing the retention time of our unknowns according to standards. But if we don't even have standards, you can still run this, because each of these peaks is going to hit the detector, which is the MS, at a different time. So the first peak is going to hit the detector, and then it's going to give us a mass spectrum. And so then the next peak will hit the detector and give us a mass spectrum like that. So when the first peak comes off, it's going to we're going to get a mass spectrum for that peak. And if you click on this, then in fact you will bring up the mass spectrum, and it will allow you to analyze it. So you might say, well, why do I even need to know how to do this when I have a library of compounds that I can compare my GC against, and I have standards? Well, if you don't really know what your compound is, if your compound's not in the library, then you're not going to have a standard for it, and you're going to need to be able to figure that out on your own. Another application for mass spectrometry is to analyze large biomolecules. So previously, like 30 years ago, these large molecules like proteins couldn't be analyzed in mass spectrometry because they were just too big. They would break apart when they were ionized with electron impact ionization techniques. So now we have new techniques that are more gentle ionization techniques that will allow these molecules to be ionized so that they can then be carried toward the detector without breaking apart. And so one of these techniques is electrospray ionization. So there's a typo here, where the high voltage needle sprays the liquid into the vacuum chamber, and that is going to cause this to be ionized, and then it will be carried with carrier gas toward the detector, and it will hopefully will be able to have a molecular ion peak for our large biomolecule. So these softer ionization techniques allow for the analysis of larger molecules.